come to more of that later. Now, you can have corresponding diagrams. Let us suppose that I take the same system and I replace pressure as the vertical axis by the molar volume. So here we have a triple point. So this is the pressure and temperature at which all three allotropes are in equilibrium. In the volume diagram, clearly of course it's the same pressure, same temperature, but now the three phases are in equilibrium, so they have to be in the same pressure, but they don't have the same molar volumes. And so here you have the three molar volumes. This is the molar volume of kyanite, sillimanite, and andaluzite at the triple point. So what you see is your triple point here has become like an invariant line because you've replaced a potential variable by an extensive property variable. And in fact, if you were to rotate this diagram counterclockwise, you would see that this is sort of like a eutectic type invariant, two-phase regions, three-phase regions. And in this case, the lever rule applies too. If you're in this two-phase region here, I can draw a tie line between the two ends, and this will give me the molar volume of this phase, the molar volume of this phase, and the relative molar volume. Okay, and one final diagram I want to show you, just to show you all the wonderful, I rotated the thing, I'm totally out of sight here. View, rotate view, clockwise. Okay, one final thing before we then go on. I'm not showing you all why this is the case, I'm just trying to show you all the different kinds of phase diagrams you can get and how these can all be, these are all very useful and they're all calculatable by the same algorithm. Here we had, this was back to the isopleth. So this was, remember, the 10% zinc isopleth as you went across the three-component system, the vertical section. Here now I'm taking this diagram. Those two diagrams I just showed you for the Al2SiO5, the PT and the VT diagram could be called corresponding diagrams. One kind of comes from the other. These diagrams here are another set of corresponding diagrams. Here I'm going to replace temperature by the enthalpy. The heat content, the enthalpy content of the phase. And now what you find is, so every point on this diagram corresponds to a point on this diagram with the same composition, the same overall ratio. Okay, but now the isotherms, these red lines are isotherms on the diagram. Okay, because two phases at equilibrium have to be at the same temperature, but they don't have to have the same enthalpy. Okay, so what's happened now is all the diagram now is, well, I won't follow the, anyway, here we have a three-phase region, two-phase regions, one-phase region. But this will now, it will tell you the enthalpy, if you were to heat, say I was to take an alloy at 80% magnesium-aluminum ratio, and were to heat it from room temperature to 125 degrees, that's the enthalpy required, 225, 325, and so on. Okay, you can follow the enthalpy required to heat the thing. So let's say it differently. Let's say I cool it at whatever this composition here, I cool it at 75%. As I'm cooling it down from 625 to 525, that's the CPDT term. Now you see that to go from 525 down to this temperature here, okay, I'm now not just cooling the liquid, but I'm also precipitating the FCC phase. Now, crossing here, this is an isothermal region. As I cross this isothermal region here, the temperature stays constant as the eutectic reaction occurs. But this has been, I should have it out. This is a bit too complicated, this one. Anyway, we'll come to another example later for a binary system that's simpler. But this can be very useful because it can tell you, if you have an alloy, you can, during casting, you can find out how much heat you have to remove to cool it down to this region, how much more heat you have to remove to precipitate the primary FCC phase, how much more heat you have to remove to take care of the eutectic reaction, how much more you remove to precipitate the tau phase. You can see what's happening. As you're cooling it, you want to know, not this diagram will tell you the sequence of phases as you cool it, and versus temperature. This diagram here will tell you how much heat you have to remove as you cross each one of these regions to go to different temperatures. Okay, so you'd like to know how much to go, as I'm crossing this region here, how much heat will have to be removed to go from this temperature to this temperature. Well, you go back up here and you can read it off here. So these are corresponding diagrams, and this interestingly follows all the rules of construction of this is a phase diagram. It contains two phases, you're just plotting different properties. And there's all sorts of other things you can plot, and sometimes they are single valued and other times they're not single valued, in which case you shouldn't plot them, and CACSAID won't let you plot them. So I want to talk a little bit more now about the phase rule, and about what constitutes a proper phase diagram. I was going to do that later on, but I think I will do that now. Okay, this was just to sort of whet your appetite a bit, to show you all the different kinds of phase diagrams you can get. And you should now be saying, how could you possibly calculate all those diagrams using one single algorithm? You would think you would need a different algorithm for every different kind of geometry, which is what we once thought. And then one day it hit us that you didn't have to do that. I think that I will stop here, but I will ask, I'm not going to give you a lot of devoir for next week, but I would like, this is getting into somewhat more complex thermodynamics, so I think it's more important now that you say read a bit, to understand better what I'm saying. If you read it ahead of time, it would be nicer. I would look at sections 3 and 7. Although in section 7, certain parts of section 7 get a little bit rough. Okay, read all of sections 3 and 7. Section 7 subsection 7.7 is maybe not necessarily if you don't, if you really like partial derivatives and things, you might go to 7.7, which is the rigorous proof of the whole thing. But you could skip 7.7 if you were so inclined. But anyway, please read sections 3 and 7 on the phase rule, because okay, if you read those and we understand those, then you understand everything there is possibly to know about phase diagrams of all sorts. That's the entire theory of phase diagrams, I think. Well, single-valued phase diagrams, anyway. And for devoir, these are pretty simple. This is just to make sure you understand interpreting binary diagrams. So you don't have to do these. Read them and see what you think if you want to look at them. But 1, 2, 3, 5, 6, and 7. And you can read the other numbers if you want and look at them, but this is basically simple stuff on phase diagram, binary phase diagrams, so you should be able to just look those over pretty rapidly. Maybe number 1 is applying the lever rule. You might find if you try to do number 1 and 2 and you thought you understood the lever rule, maybe you don't. But the rest are straightforward. So that shouldn't take you too long to do the devoir. I really, in this case, do encourage you to read 3 and 7, because otherwise, well, it would help a lot for next Tuesday and Thursday if you had read those first. Okay. Any questions about these phase diagrams in general? Because what this is all about, section 3 is the phase rule and its whole classical thing. What the phase rule really means. It's one of the most misunderstood rules in phase diagrams. Number 7 is this whole thing. Now, how do you calculate this with a single algorithm? What are the rules that determine the geometry of phase diagrams and so on? And it's a unified theory of phase diagrams. These phase diagrams are not different. They all follow exactly. All the diagrams I showed you and many others follow, although it doesn't look like it, they follow exactly the same geometrical rules of construction. Some of them are limiting cases, that's all. Yeah.
Is it possible that the binary phase diagram be quasi in a specific composition range and like in the that side and the
Oh,
other
yeah, sure,
side.
of course.
So we have to first look at the ternary and then we can say, okay, it's quasi.
Well, you usually know from your knowledge of chemistry. I mean, this is usually not a big, I mean, like CaO, SiO2, from your knowledge of chemistry, you know pretty well that you're not going to get any phases in that diagram that aren't containing CaO and SiO2 on that section. But yeah, I mean, it's an experimental thing. It depends on the system. There's no way of knowing ahead of time in principle, but usually, I mean, you would know if you mix sodium chloride, potassium chloride, you're not going to you're not going to deviate from the line, NaCl, KCl. You're not going to suddenly get a phase that contains extra chlorine or extra sodium, or you're going to stay on the line. If you're mixing three metals, it's pretty unlikely that you're going to get a quasi-binary section. You can now, there's not, well, okay, I see what. Maybe I wasn't quite right. There are cases where you don't know. Let's say you take SiO2, CaO, MgO. That is already that's a quasi-ternary section in a four-component system, all right? Okay, so now we're in a quasi-ternary. Okay, so a quasi-ternary, all tie lines lie on that. Okay, there's nothing that goes outside that plane. Calcium's always 2+, magnesium's 2+, silicon. But, well, one thing, I'll talk about that on Tuesday. I mean, if I have FeO here, now, this already is not a quasi-ternary section, because as you change the oxygen content, the 2+ and 3+ ratio can change, so that's not quasi. That's only a quasi-ternary, well, that is a quasi-ternary section. But if you have calcium oxide, well, you know the calcium is almost always 2+, magnesium 2+, silicon 4+, you don't deviate from the oxidation states. Okay, if you have something that has two oxidation states, though, like iron, then right away it's very unlikely you're going to hit it. But okay, even in this quasi-ternary system then, there are some quasi-binary sections and some aren't. So in other words, it's not quite clear now, as I went from magnesium silicate to calcium silicate. Okay, and I'm going to have MgSiO3, and over here I have CaSiO3. Now, is that section quasi-binary? Is that section quasi-binary? There you probably wouldn't know ahead of time. Okay, sometime. I do believe that this one is, but this one isn't. Okay, so it depends, again, it can even depend, as you said, on the composition range or on the temperature range. Okay, so there are some regions where in this system everything is sort of like this, but in this region, not necessarily the case. But I mean, it's perfectly possible that you can have an overall composition on this orthosilicate joint, but what you really have is you have a metasilicate in equilibrium with a monoxide phase. You could have a solid solution here in equilibrium with this solid solution, just such that the overall composition is here. So the overall composition's here, but the two phases are here. Or you could have two orthosilicates. So, yeah, that then becomes experimental. You can't just assume it. Just because these are nice stoichiometric looking compounds, there's no way, there's not a proof that that's going to be a quasi-binary section. But if you looked at the phase diagram and, well, you looked, it's even possible it could look like a binary phase diagram and not really be quasi-binary, but that's pretty unlikely. At least when you look at it, you can figure what's going on. Certainly if you have two oxidation states, though, that people make that mistake. You'll see FeO, and it's not. Now that is a quasi-ternary diagram if you fix PO2. But that's another story. That's very much like the iron-nickel-oxygen one. As you're if you fix PO2, you can't write FeO-MgO because this won't necessarily be FeO. It could be it'll vary between FeO and Fe2O3, but it still will obey the rules of a ternary diagram because all phases have to be at the same PO2. If that makes any sense. Or you can see the diagram sometime in equilibrium with iron. So you have this slag FeO-MgO-SiO2 in equilibrium with a metallic phase. That fixes the activity of iron. So it does look, again, like a ternary diagram. Because all phases in equilibrium have the same activity of iron, just like they have to have the same PO2. But I'll show you this next week. This is where these things can get kind of complex. Especially if you have 4 or 5 oxides. How do you interpret a phase diagram? You'll see this in the book, in the phase diagram through Cerements. They'll plot the Fe2O3 MgOSi2O diagram at PO2 equals 0.5 atmospheres. They'll say, here it is, and there's your phase diagram. But what do they mean? You know this isn't Fe2O3, because if the PO2 is 0.5, you're going to have regions in which you have FeO. So what does it mean? What does it mean, the Fe2O3 silicon magnesia diagram when PO2 is 0.5 atmosphere? How do you interpret this thing? If I'm in a two-phase region, what's it mean? What phases is it? So I'll talk about that. This is one of the biggest problems, I think, with oxide diagrams, is when you get the different oxidation states, people, when they're plotted wrong, they're misinterpreted, they don't understand. So anyway, please read sections 3 and 7, skip 7.7 if you get bogged down, and see you Tuesday. Probably sometime soon we should, I'm pretty well nearing the end of classical thermodynamics thing before we get to solution theory, so maybe we should have a test sometime in a couple of weeks. We'll talk about that next Tuesday. You're already finished, so that's it.
No, we'll close now.
We're gonna close it anyway? Okay.
Continue.
One, two, three, stop.